Today we are going to discuss another important topic, that is flow cytometry in the benign disorders. So we already discussed the components and what are the principles, everything regarding the flow cytometry. Now we will discuss its applications, especially in the benign disorders. Okay, let's start. So in the flow cytometry applications, especially in benign disorders, again they are classified into RBC disorders, WBC disorders and the platelet disorders. Okay, then we are done with the RBC disorders. Next we will discuss the WBC disorders. What are the WBC disorders? The sepsis we can detect by flow, the primary immunodeficiency disorder, which is very important. Believe me, this was my final year exam second paper question, 10-mark question they have given. Give me write the details all about the flow cytometry in PIDs, the primary immunodeficiency disorders. Then HLH, how we'll use flow, how we will use the flow in HLH. Then ALPS, autoimmune lymphoproliferative syndrome, bone marrow failure syndrome, we'll discuss one by one. Okay. Then in sepsis, so sepsis, it is because of infections. We all know in the sepsis the neutrophils will increases, right? There will be neutrophilia, right? So but what will happen, there is a changes in their expression of these neutrophils. The neutrophils in sepsis, they show increased expression of CD64 marker. Okay, and this is one thing. And one more thing also, the monocytes, they will show decreased HLA-DR expression. So with these two markers, they have made a sepsis index. They have made a formula. Okay, the formula is the neutrophil CD64 divided by the monocyte HLA-DR. So with this ratio, if you do the flow with these two markers we did, then we can make a ratio. If the ratio is high, that means CD64 is high and HLA-DR is low. That means the patient is having sepsis. Correct? So by using flow, we can determine the patient is having sepsis or not. Okay? Yes. Then this is the main important one, the PIDD, primary immunodeficiency disorders. So flow, it is diagnostic. It is very much diagnostic in most of the primary immunodeficiency disorders, and it also helps in guiding the next whatever the molecular analysis to do, in which syndrome, what gene we have to test. Okay, all this it also guides the clinician to go for the molecular analysis. But the major pitfall, the major caveat for the flow cytometry is simple. So flow cytometry, we are checking for the proteins, nothing but antigen, nothing but proteins. We are giving antibodies against those proteins and we are checking. Okay, if the protein is absent, then there won't be any staining and there won't be no fluorescence. Okay, we can detect it. But in some PIDDs, the protein will be there, but the protein is non-functional. That means dysfunctional or non-functional protein. The protein is present, but it is not functioning. That time flow is useful. No, right? Because flow will detect if protein is there, we are giving the antibody, antigen is already there, they will bind and fluorescence will come and will label the patient as absolutely normal, even though the patient having disease. Okay, so that is a major drawback for this flow cytometry. It cannot able to identify the disease which are due to non-functional proteins or dysfunctional proteins. Only in protein absence only we can identify, but in these disorders we cannot identify, which is a major drawback of the flow cytometry. Okay, then. So how will you approach for this PIDD? Yes. So primary immunodeficiency disorders, yes, there are neutrophil disorders, and majority we have divided into PIDDs into three types, right? Leukocyte disorders, right? Leukocyte disorders, then this complement disorders, then the B and T cell disorders, correct? So these three disorders are there, right? So for this, so what will be there? There will be leukocytes or B and T cell disorders. So there will be lymphocytopenia, right? There will be lymphocytopenia. So there will be lymphocytopenia and sorry, let me change the color. Okay, so there are lymphocytopenia will be there, right? So if there is persist lymphocytopenia or in leukocyte disorders, there will be neutrophilias if they are there. After excluding the infections, autoimmune disorders, everything, then we have to go for this flow cytometry analysis. We have to rule out first all other causes of this cytopenias. Okay, not before not doing all the things directly, you should not go for flow. Okay, then after excluding everything, we are analyzing this. What we are doing here, lymphocytopenia. So we are analyzing these T cells, B cells and NK cells. So what is the marker for T cell? It is CD3, that is specifically it is cytoplasmic CD3. Then for B it is CD19 and for NK it is CD56. Okay. We are analyzing this, and if these subsets are deficient, then if the lymphocyte subset deficiency is there, if both CD3 and CD19 are deficient, then it is severe combined immunodeficiency, correct? And if T is there, only CD3 is deficient, it is Digox syndrome, and if it is B is deficient, it is X-linked A gamma globulinemia. We'll discuss each and everything, don't worry, I'll explain everything. So here is the flow, how we'll approach it. Okay, if the lymphocyte subsets with these markers are defective, if the protein, cell surface protein is defective, that means if the leukocyte addition defects, yes, what is the protein defective? In the LAD, it is beta 2 integrin, correct? Yes, beta 2 integrin is defective. If that is defective and hyper IgM, these disorders also we can detect by using flow. Then if the intracellular protein defect, see here, everything the protein is absent, then those things only it is able to identify, flow is able to identify. Okay, so Wiskott-Aldrich syndrome, VAS protein, if the protein is absent, Wiskott-Aldrich syndrome will come, we can detect. Then the functional defect, again don't confuse here, this is not the functional protein defect. Here the functional defect means the function of the RBC, I'm sorry, the function of the WBCs are abnormal. Okay, so the example, I can tell you the example so you can understand. It is chronic granulomatous disease. So the neutrophils, the NADPH oxidase enzyme is not absent here in CGD, right? So the enzyme is absent, the protein is absent. So we can able to identify with the flow. Okay, the function of the WBC is abnormal, that is chronic granulomatous disease, where we'll do the DHR assay by the flow. Okay, yes, we'll discuss one by one. So first the one SID. Okay, mainly the X-linked SID. X-linked SID. So what is the defect here? In PID it's very simple. Okay, we should know what is the defect first thing, and for the defect, for what any CD marker is available or not. That much only we should know. Okay, so what is the defect here? Here, yes, X-linked SID. Here the common gamma chain. The common gamma chain for the interleukins that is absent. So especially the interleukin 7. So this common gamma chain, it is absent. So when this gamma chain is absent, the interleukins are not produced. Okay, interleukin 2, 4, 6 and 7, these are not produced. And mainly if these are not produced, what will happen? This interleukin 7, it is required for the T cell development. This is required for T cell development. So for the development of T cells, this interleukin 7, it is required. Okay, when this interleukin 7 is not there, T cells won't develop, and if the T cells won't develop, again, it in turn, B cells won't develop. Because for the proper development of B cells, these T cells are required. Okay, so if T cells are not developing, automatically B cells also won't develop. So both B and T combined defect is there. So that results in the severe combined immunodeficiency, SID. Okay, so yes, so here we have to detect the T and B cells. So what is the marker for T? It is cytoplasmic CD3, and for the B it is CD19. So if you see here, the CD3, how many cells are there? Only 6% of cells, entire lymphocytes, they are expressing CD3. And CD19, none of them, not even 1%. Okay. So majority, both CD3 and CD19 are negative. That means B and T cells are not forming. So it is SID. We can identify both combined deficiency is there. One thing. And the common gamma chain. So we have to know the defect and what is the CD marker for it. So for this common gamma chain, the CD marker, it is CD132. That is the CD marker. So we are doing the CD132, and here I kept the control here. Can you see the CD132 almost 10 to the power of 4, that much of high fluorescence is shown by the person. So that means he is absolutely having the normal gamma chain is present in that person. So he is normal. But in the patient, if you see, there is no fluorescence. That means the gamma chain is absent. So the CD132, it can't go and bind to the gamma chain. That means that to its corresponding antigen. So there is no fluorescence. Okay, it's as simple. You should know the defect and any CD marker for it. Okay, SID is done. Then for the B cell defect, that is X-linked A-gamma globulinemia, Bruton's X-linked A-gamma globulinemia. So what is the defect here? Yes, it is the BTK enzyme, right? Bruton tyrosine kinase enzyme. So what is this enzyme will do? It causes conversion of precursor B cells into mature B cells. Okay. So for this conversion, this enzyme is required. If this enzyme is not there, what will happen? The mature B cells won't form at all. So what will happen again? If you do the B cell markers, CD19 and CD20, can you see? Only 0.2% of cells only showing this marker. That means only 0.2% B cells only there. Rest all, they are negative. Okay, so B cells are completely not there. If B cells are not there, then in the lymph node there won't be lymphoid follicles and plasma cells, nothing will be there in the X-linked A-gamma globulinemia. And again, the defect is enzyme, so we can do the enzyme. Okay, cytoplasmic enzyme marker. BTK is the enzyme. So can you see here, whatever it should be seen on the extreme right, you can simply blindly you can remember like that also, but that is the concept here is the fluorescence here. Okay, whatever is coming more fluorescence, that is normal, but you can simply remind whatever is towards the extreme right, that is normal. So here in the patient, it is coming towards the extreme right, so this is normal. But see in the patient, it is not showing any fluorescence. Even at the 10 power 0 it is there. So this is the patient. And carriers, who are the carriers here? It's X-linked disorder. So females are carriers. So in the carriers, can you see one gene or two genes will be there, one gene is lost and one of the gene is normal. Okay, so his carriers will show this kind of intermediate reactions. Okay, so this is Bruton's X-linked A-gamma globulinemia. We can do the BTK enzyme and we can do the B cell markers, which will be negative. Okay, then next one. So we are the Digeot syndrome, the defect is Cas22, right? The mnemonic is Cas22, deletion 22. So it can be detected by molecular methods, not by the flow. Okay. Then, so we're done with the subset defects. Now we are discussing the cell surface protein defects. That is leukocyte addition defect. LAD is leukocyte addition defect type 1. So what is the defect here? I already said it is beta-2 integrin. Correct. So what is the CD marker? We should know the CD marker. What is CD marker? Yes, it is CD11C or CD18. Okay, so what on which cell we have to check here? Which cell? It is neutrophils, right? Because leukocyte, the addition, aggregation, rolling, addition, rolling, movement, homogenization, all these by the neutrophils, right? From the vascular compartment to the site of infection, correct? So on the neutrophils, we have to check for the CD18 and CD11C. And again, which one is normal, which one is abnormal? The blue ones, this is normal. And this one, as I said, the extreme left one, this is the patient. Okay, CGD type 1. Okay, the expression is not there. Okay, this is the patient and this is the normal. Again, this is the normal and this is the patient. Okay, so we can do and gating of these neutrophils, obviously we can do with the forward scatter versus side scatter, the high side scatter one of the neutrophils, or we can use the CD45 versus side scatter, where also we can separate the neutrophils and we can gate those neutrophils. Then on these neutrophils, they are gating again CD18 and CD11C, which they will not show any fluorescence. Okay, LAD type 1, it is done. Then what is another cell surface protein defect? That is hyper IgM syndrome or X-linked hyper IgM syndrome. So what's here? First, what is this? Before knowing what is this, we should know the normal. What happens when there is infections in our body? What will happen? These antigens will be presented by our antigen presenting cells, APCs. Nothing but those are dendritic cells, okay, Langerhans cells, all this. So they will present to which cells? CD4 positive cells. That is nothing but T helper cells. So when they present this T helper cells, they become activated, right? So when they becomes activated, and these T cells, they will in turn activate the B cells, okay? Because these B cells will produce the immunoglobulins, and they will go and react to these antigens, the proteins produced by the microorganisms. Then they will eliminate the pathogen, right? So these B cells, these T cells, they will activate these B cells. And how they will activate? This is the main interaction, which is CD40 ligand versus CD40 interaction. And the CD40 ligand, which is present on which cell? This is again a potential MCQ. CD40 ligand is present on which cell? It is present on the T cells. Okay, I used to remember like more L is there. So T cells are there dominant. They need more. They are very extra powers, right? So they have the CD40 ligand. L is the extra number is there, extra letter is there. So they are present on the T cells, okay, and CD40 is present on the B cells, okay. So this interaction is important. When this interaction is happened, then these B cells, what will happen in the B cells? The B cells undergo class switching and the affinity maturation. So what is this class switching? So when I said the precursor to mature B cells, these mature B cells, they are also called as naive B cells. Mature B cells also called as naive B cells. So these naive B cells, they will express only IgM and IgD. They'll express only this, okay, but these are naive B cells. What is this naive B cells? Naive means they are not exposed to antigen till, okay, they are not exposed to antigen, okay. When they exposed to antigen, then all these steps will happen, okay. The T cells will get activated, this interaction will come, and this class switching means when this antigen exposed to B cells, they will convert into plasma cells, and they will produce the antibodies, and these antibodies will be different classes, not the IgM. They will produce IgG, IgA, IgE, depending on the infection. If the infection is bacterial, IgG will produce. If the infection is by parasites, then IgE will be produced. And if the infections are affecting the mucosal surfaces like genitourinary or gastrointestinal, that times IgA will be producing more, okay. Based on the infection, this class switching, affinity maturation, all these things will happen only when the T cells are activated. T cells activate these B cells with this CD40 ligand and CD40 interaction. So this whatever till now we discussed, this is normal, completely normal. So when this normal things doesn't happen, then this results in this syndrome, that is X-linked hyper IgM syndrome. What is problem here? The CD40 ligand, okay, the T cells CD40 ligand, that is defective, okay. So when this is defective, where the stimulation won't be there, the naive B cells will remain naive B cells, so they will have only IgM and IgD. So even the infection is there, this naive B cells only proliferate and they will produce only IgM antibodies. That's why the name is hyper IgM syndrome. They won't have IgG, IgA and IgE. Why it is syndrome? Because these IgM antibodies, they are pentavalent, right? So what they will do? Pentavalent, they will cause agglutination of RBCs, okay, they will block the blood vessels and they will cause gangrene of the limbs, everything. So many symptoms will be there, okay, that's why it's a syndrome, okay. So this will happen in this one. So what we have to do here? Again, we have to detect this flow. How can we detect? Simple, right? We should give antibody against this CD40 ligand, okay. Yes, we can detect the in flow cytometry. So how will we detect? Yes. So here we are getting the population CD3, the CD3 positive lymphocyte. That means nothing but T cells. T cells are defective. CD40 ligand is present on T cells. So we have to separate the T cells from the rest lymphocytes. This can be the CD3 negative. This can be B lymphocytes or NK cells. Anything. They are CD3 negative, right? Then. So these T cells we have separated and we are getting against the CD40 ligand. So what is this unstimulated and what is this? So here when this CD40 ligand will be expressed, normally it won't express. It will express only when there is infection. Okay, but that is normal in our body. But to detect in flow cytometry, how will we create that infection kind of situation? How will we create? We can't infect the flow cytometry. We can't infect the machine, right? So how will we create? We are creating by adding this chemical, that is PMA. What is this PMA? It is Forbol 12 myristate 13 acetate. PMA, Forbol 12 myristate 13 acetate. This is the chemical. What this chemical will do? It will activate the T cells. It will activates. That means it acts as an infection. Okay. For the activation of these T cells, we are adding this PMA along with the calcium, so that the T cells will get activated. When this activated, then only they will express the CD40 ligand. Normally they won't express. Okay. So this is the initial one, that is unstimulated one. That's why they are not showing any CD40 ligand expression. Only the T cells are there. Here, see, can you see no CD40 expression? Then these CD3 cells, when the T cells, when they are stimulated by this PMA and calcium, then they are expressing the CD40 ligands. Can you see these cells? There are more clump here. Then they are starting expressing, and almost 26% of the cells have expressed this CD40 ligand. So this is normal. This is a control population. Okay, this is a normal. So if the patient has hyper IgM syndrome, what will happen? So XHIM is X-linked hyper IgM syndrome. Okay, what will happen if the patient has this hyper IgM? See, initially this is unstimulated one, again unstimulated one. Okay, so CD3 again obviously unstimulated, so everything will be, they won't express any CD40. Then we are adding, again what we are adding, PMA and calcium ionophore. We are adding those two. Right? So what will happen here? We have stimulated, the T cells are stimulated, but after stimulating also, see, less than 1%, even less than 1% of cells, they are expressing this CD40 ligand. They are not, none of the cells, most of the cells, they are not expressing the CD40 ligand. That means CD40 ligand is defective. That's why this patient having X-linked hyper IgM syndrome. Understood? Yes. Then there is the next syndrome. We are done with the cytoplasmic cell surface proteins also. Now we are discussing the cytoplasmic intracellular proteins, cytoplasmic proteins, that is VASP protein. Okay, VASP. Cytoplasmic protein, see, VASP protein. Okay, Viscott-Arledge syndrome protein. So, simple. If this protein is absent, then it will cause Viscott-Arledge syndrome, right? So, here, this is the control. Again, normal population. Can you see? The control, the positivity percentage around 99% of cells. 99% of cells, they show the positivity of this protein. Majority of cells has expressed and they show the high fluorescence also. So, this is normal. But if the patient, see, same thing. Patient, only 27% of cells only has taken up the stain. So that means the VASP protein is defective in them. Okay, that's why there is no stain, no uptake of the stain, and there is no fluorescence is also very less. Can you see very less fluorescence? This is the fluorescence one. Blue one is the fluorescence one. Less fluorescence has been there. Okay, so this is Viscott-Arledge syndrome. Here, what is the triad? What is the triad for Viscott-Arledge syndrome? Yes, yes. Anyone? What is the triad? Yes, there is recurrent infections, and yes, eczema. Eczema will be there. Then there will be thrombocytopenia. Correct? This is the triad. And again, one more question. Which platelets will be there? Small platelets or giant platelets? Viscott-Arledge syndrome, it is small platelets. Okay? Microthrombocytopenia will be there. Okay? Yes, this is a triad of the Viscott-Arledge syndrome. Nothing, we have to look for the protein. We will give the antibody against this protein, cytoplasmic antibody. Then, if the protein is present, then there will be fluorescence. If it is not there, there will be no fluorescence. Simple? Then. The last one, it is the functional defect. That means here the function of the WBC, that is not normal. Okay, chronic granulomatous disease. So what is this disease? Because there is no NADPH oxidase enzyme. That is the defect. So what will happen normally what will happen? NADPH, what it will do? It will convert the oxygen to superoxide radical. Okay, this conversion is by the NADPH oxide. Then this superoxide radical, it will converted by superoxide dismutase to H2O2. Then this will act upon by the MPO here, then that forms the finally hydroxyl ions. Finally here free radicals are forming. So when this happens? When there is infection in the neutrophils all inside the neutrophils all these reactions are happening. Okay, so when there is infection, the neutrophils all they engulf the neutrophils, monocytes and all, they will engulf this whatever the pathogen, and they will produce these free radicals, and these free radicals will damage the organism, will damage this pathogen. Okay, eliminate this pathogen. Okay. So this is normal. So when there is no NADPH oxidase, what will happen? These free radicals will be formed? No, right? They won't form. And because of this, there is no free radicals. They won't kill the pathogen, and that results in this chronic granulomatous disease. Correct? So what we are doing? Again, this NADPH oxidase is absent, right? So we are checking for this one only. How we will check? Yes. So what we are checking for this? How we are checking? In the indirect way. How we are checking? Here, see, we are taking the neutrophils, and the cells are neutrophils. Okay. Then we are adding dihydrorhodamine. DHR is dihydrorhodamine. Dihydrorhodamine. It's nothing but a dye. Okay, we are adding this dye. So here again, unstimulated one. Same thing. Whatever happened in the previous unstimulated, where we are adding the infection type of environment we should create in case of hyper IgM. The same thing here we have added the cells, and they are unstimulated. Then we are stimulated. That means we have to create the infection. This NADPH oxidase, it will express only during infections, not normally, right? So we have to stimulate by using same thing. Forbyl 12, myristate 13, acetate, PMA. Okay, and calcium ionophore also. Okay, so we have to stimulate. Then what happens? The stimulation happens, then neutrophils, they will produce monocytes, and they will produce NADPH oxidase, and finally free radicals are produced. And these free radicals, what will happen? These free radicals, whatever produced, these free radicals, OH minus is produced, it reacts with this dihydrorhodamine. Okay, it reacts with dihydrorhodamine, and it converts this dihydrorhodamine to rhodamine. Okay, this rhodamine is fluorescent. Okay, now you understand the concept. Anything finally should be fluorescent, then only we can able to detect in the flow cytometry, right? So here the dihydrorhodamine, the conversion of this dihydrorhodamine to rhodamine, it happens by when there is free radicals is available in the cells of the patient. Okay, then only this conversion will happen. If there is no free radicals, that means there won't be no conversion, there won't be fluorescence. And if the free radicals are producing, that means the patient having NADPH oxidase enzyme. Then only the free radicals are producing. If the patient don't have the NADPH oxidase, then there won't be no free radicals, and no free radicals, no fluorescence. No conversion of DHR to rhodamine, then there will be no fluorescence. Understood? The same thing here. This is a healthy control. Can you see unstimulated cells? Then when we stimulated it, see they have fluorescence. It is going beyond 10, almost reaching 10 power 4. Okay, here they will calculate this neutrophil oxidative index. Nothing but the ability of the neutrophils to produce the free radicals. The oxidation means that to produce this, to convert this oxygen into free radicals, how much ability the neutrophils has. Okay, here because they have more ability, more amount of cells are producing this NADPH oxidase, and all this they converting into free radicals, and the free radicals are reacting with this rhodamine, and more fluorescence is coming. Okay, this is control patient. But if you see the control person, okay, then this is the patient. If you see in the patient, again the unstimulated ones, but the stimulated ones, if you see, it is even after stimulation, there is no NADPH oxidase, no free radicals, no conversion. That's why no fluorescence. No fluorescence. See the neutrophil oxidative index. This is neutrophil oxidative index. NOI neutrophil oxidation. It is almost, it's almost nothing. It is not releasing any fluorescence because there is no conversion, there is no free radicals, because there is no NADPH oxidase. So it's going back in reverse way, in the indirect way. We are identifying the condition. Okay. Yes. We are done with all the PIDs. It's little, maybe you first time if you are listening, it will be little clumsy. Again, I want you to pause the video, go back and again listen the video. Then you will understand clearly. Okay. Yes. Then we'll go with the third one, the third WBC disorder, HLH. Okay. How the flow is useful in identifying the HLH. Okay. So HLH, what is the defect? Yes, the CD8 positive cytotoxic T cells and NK cells. These cells are abnormal. Correct? Whatever their function they should normally do, they are not doing that. That's why, so what is their normal function? They are like the army, right? They are the army of our body. So whenever any invader comes into our country, our army will kill them, right? In the same way, in our body, the CD8 and NK cells, their army, any pathogen enters, they will kill them. That is their normal function. If an army doesn't work, what will happen? The invaders will come and they will damage our country. The same thing happens in the HLH. These are not, the army is not normal. They are abnormal. So they are not doing their function. So the infections, they will come and they will damage all our tissues. That will cause entire activation of all the cytokines and all that results in the HLH. That is happening. So what these army people, they have guns, right? So normal army people. But for our body army people, the CD8 T cells and NK cells, what they have guns? They have perforin, which is like a gun. Okay, this perforin, what it will create holes in the whatever the pathogen invading. It creates the holes in the pathogen and kills the pathogen. So they will secrete this perforin. So we are checking this only in the flow. So we are giving antibody against this perforin and we are checking the perforin levels in the patient. Okay. So normally this is the control. Okay, this is the control. So normally, and among these T cells and NK cells have capacity of producing more perforin than the CD8 positive T cells. Okay. So NK cells normally around, see the perforin enzyme, almost 95% of cells they are showing this perforin enzyme. That's why there is high fluorescence. Okay. Antibody we have given against this perforin. There is antigen antibody complex formed and fluorochrome is activated. Then the fluorescence came. Okay. And in the same patient, where are you doing this? The perforin only. Perforin. So here can you see only 1% of cells only showing the perforin expression. Okay. That means the NK cells they are defective. Okay. Then again CD8 positive T cells. Again this is the control. And as I said, the NK cells have more expression, shows more expression of the perforin than the CD8. Only 23% of cells, that is still it is normal. Okay, some cells they are showing the perforin expression. See here the fluorescence, but here can you see none of the cells in the patient. This is the patient. None of the cells are showing any fluorescence. Okay, so that means the T cells, cytotoxic T cells and NK cells are defective. They are not doing their function what they are supposed to do. So that's why the patient is having susceptible to more infections and activation syndrome results in the HLH. So within this way we can detect the HLH. Okay. Next one, the ALPS, autoimmune lymphoproliferative syndrome. So what happens here is there is defect in this fast mediated apoptosis. Which pathway? This is extrinsic or intrinsic pathway of apoptosis? This is extrinsic pathway of apoptosis. Correct? This is extrinsic pathway. So why this? What happens if this pathway is defective? When the apoptosis is defective, then what will happen? So whatever the cells they are supposed to die, they are not dying. Right? Why the cells should die? So for this, you should understand we will discuss before the lymphomas, I will discuss the T cell development and B cell development clearly. So here I will explain a little bit. So normally during the development of B cells, even T cells, so what their function? They are immune cells, right? What their function is? After development, they should go and fight. They should identify the pathogens and they will kill them. So the same thing for they will get trained for during the development. They will get training for the same thing. Okay. So what they will do? These developing T cells, they will expose to different antigens. Okay. They will expose to our normal antigens also, our self antigens also, and the foreign antigens. Both they will express. Okay, they will expose, not express. They will expose to both the normal antigens and to our self antigens and also to the foreign antigens. So when they are exposed to these antigens, what they should do? They should identify only the foreign antigens, right? They should not identify our self antigens. If they identify, what will happen? Autoimmunity occurs. They will damage our self antigens and autoimmunity occurs. That should not be happen, right? So, but normally what will happen when they expose to this? Some cells they will react to the self antigens also. But those cells they should develop further or not? They should not develop further, right? Correct? So those T cells which they react to the self antigens, they are called autoreactive T cells. Autoreactive T cells. That means the T cells which are reacting to our self antigens, they are called autoreactive T cells or autoreactive B cells. And these T cells or B cells, autoreactive cells, they should undergo death by apoptosis. They will die with this apoptosis mechanism, specifically the extrinsic pathway only they will die. Okay, so when this pathway is defective, let's say this pathway is defective, what will happen? The autoreactive cells, will they die? No, right? So these autoreactive cells, they won't die and they will proliferate. Okay, so this proliferation of this autoreactive double negative T cells, that means initially during the development, the T cells won't have these markers. Finally, they have CD4, CD8 T cells, cytotoxic T cells, they are forming, right? Initially, they won't form, they don't have this all these markers. So they are double negative T cells, then they become double positive, then after that they will become single positive. We'll discuss everything in the development. Okay. So, since these double negative T cells, they will be, these autoreactive double negative T cells, they will be proliferating. So, what will happen? These autoreactive, they will go and damage our self tissues. So, they damage our multiple self tissues, they will damage, and that results in this autoimmune lymphoproliferative syndrome. So, there is autoimmunity because they are reacting to self antigens, and who are reacting? The lymphocytes, and they are proliferating. Yes, these autoreactive cells are proliferating. Why they are proliferating? Because they are defect in the, there is defective fast mediated apoptosis. That's why they are proliferating, and they will going and damaging our own tissues, results in this ALPS. Okay. So, here now you tell me which one we have to detect. We have to detect these autoreactive double negative T cells we have to detect. So, which markers we can use? Obvious, right? We can use CD8, CD4 and CD8. Okay, if these two markers if you use, if these two markers are negative, then they are double negative T cells. If they are more, then it is abnormal. They should not be there. Okay, if they are more, then it is ALPS. How much more? Okay, there is a cutoff. Okay, normally, like if these double DNTs, it should be less than 1.5% of total lymphocytes. All T cells, B cells, NK cells for the total lymphocytes, they should be less than 1.5%. And for the in only the CD3 positive, if you take only the T cells, then they should be less than 2.5%. That is normal. Okay, I'm telling the normal. Can you see that this is the control normal? How much is the percentage of this? Here on the y-axis, both CD4 and CD8 markers. On the x-axis, the alpha beta T cell receptor. These are the gating markers. So the CD4, CD8, both positive cells. These are the both positive cells, double positive, right? Q2 zone, right? Double positive zone. Right, double positive zone. So majority of the cells, they are positive. Only 1.1% of cells, they are double negative T cells are there. So it is less than 1.5%. So normally less than 1.5% of all T cells. Okay, all T cells, or less than 2.5% of the CD3 positive T cells. Okay, then it is normal. Okay, but in ALPS, can you see this is the ALPS? Okay, can you see? Here, the double negative cells, both CD4, CD8, this quadrant, only alpha beta T cell receptor is positive and these two markers are negative, right? This is the Q3 zone, right? So, this is only the X whatever the marker that is present on the X axis, that is positive, and Y axis is negative, that is this quadrant, Q3 quadrant, right? So, here the alpha beta T cell receptor positive, that means these are T cells, okay, and around 15.7% of cells, they are not showing the CD4 and CD8. Usually, it should be less than 2.5%, right? Normally, it should be less than 2.5%, but here around 15% is there. That means abnormal, that is that patient is in ALPS. Okay, so the cutoff is if it is more than 1.5% of total lymphocytes or more than 2.5% of CD3 positive lymphocytes, then it is ALPS. Okay, done. Then the last one in the WBC disorder, that is bone marrow failure syndromes. What are the most common bone marrow failure syndrome? Yes, it is Fanconi anemia, right? So Fanconi anemia, what is the problem? What is the defect here? Again, we should know the defect, then we can understand the what marker, what thing we have to do in the flow. So in Fanconi anemia, what is the problem? There is Fanconi, FANCA, FANCA. Okay, that FANCA gene is defective. So what will happen? There is double stranded DNA breaks will be there when the cells are exposed to DNA cross-linking agents like mitomycin C or DBA, right? When these DNA cross-linking, when the cells are exposed to DNA cross-linking agents, when what will happen? These cells are defective, right? Then Fanconi anemia. So there will be double stranded DNA breaks. Okay, even the normal cells also shows the double stranded DNA breaks. But what will happen when there is double stranded DNA break? When there is DNA break, okay, what will happen? Who is the policeman or guardian angel of the genome? Yes, it is P53. So the P53 will activate it, right? What it will do? It will blocks the cell cycle, correct? This is all there in the general path. Okay. So this P53 blocks the cell cycle. At what stage? At what stage? S and G2 phase. That is the phase where this P53 is guarding, right? Yes. So in this phase, it will blocks the cell cycle. Then what it will do? Why it is blocking? Why it is stopping the cell cycle? Because to repair the DNA break. Okay. So in the normal patients, when we add the mitomycin, there will be DNA breaks, and the P53 is activated, and it will repair the DNA damage, and then the cell cycle will be continued, right? But in Fanconi anemia, this repair mechanism will be defective, correct? Because the FANCA gene that is defective, that is mutated. So this DNA breaks, they are not corrected. What will happen? The cell cycle will be arrested. Right, so the cell cycle arrested the late S, the cell cycle arrested late S or G2 phase, correct? So then the cell cycle won't continue further. But and you also know in the S phase, what S is a synthesis phase. The DNA will get doubles, right? So because of these breaks and all the doubles, the DNA content in the G2 phase, it will be more. Okay, so they will in the flow cytometry, they will give the DNA binding agents, DNA binding dyes. Okay, so in the normal phase, this is a control, mitomycin C is applied, DNA breaks happen, but the patient has a normal P53 everything mechanism, so it is corrected and the cell cycle is continued. That's why the DNA content, this is the DNA content in the G2 phase, it is less. But in Fanconi anemia patient, the repair mechanisms are not normal. So what will happen? The cell cycle is arrested. The cell is arrested at this G2 phase only. That's why the DNA content, as this G2 comes after the S phase, the DNA content is also more, and DNA breaks is there, so it is arrested, and the DNA content will be more, and which is classical for this Fanconi anemia, and this can be detected by the flow by using the DNA binding dyes. Okay, understood? Yes. Then we'll go to the final disorder, that is platelet disorders. So what are these platelet disorders? Yes, Bernal-Soler syndrome and Glasman thrombasthenia. So here only you can tell me what is the defect in the Bernal-Soler syndrome? Yes, it is GP1B9A, right? 1B9A. 1B9 or 1B95. This is the receptor that is defective. So what is the CD marker? We should know the CD marker. So GP1B, right? So it should not be 1 here. In the CD marker, it is 42A/B. A is for alpha, B is beta. Okay. GP1B, it has receptor has alpha chain, beta chain, and the GP1B9 and 5, everything will be there. Okay. So the GP1B, so 1 should not be coming in the CD marker. So it is CD42, and A for A, alpha, and B for beta. Okay. So this is the CD marker, and we'll test this marker. Okay, in the flow cytometry. And Glasman thrombasthenia, what is the defect? Yes, it is GP2B3A. That is the receptor that is defect. So 2 means 2 should not come. So I used to remember like this. 2 should not come. So it is CD marker, it is CD41. Okay. And for 3, it is CD61. Okay. 2B is CD41, 3A is CD61. So these are the CD markers. And we will look for the markers in flow. If these markers are positive, fluorescence will come. Then the patient is normal. If these markers are deficient, then the patient is having the BSS or GT. Correct? So the same thing only. So the Bernal-Soler syndrome, the blue ones, that is the normal, and pink ones are the patient. Okay. Can you see in the Bernal-Soler syndrome, the defect is GP1B9 and 5, GP1B9 receptor. So the CD marker is already said CD42A and CD42B. Can you see this is CD41A61? It is which receptor? GP2B3A, right? But in BSS, this is absolutely normal. The abnormal is this one. This is abnormal. So that's why, can you see the CD41, 61, even the patient and the healthy control, even the patient has more than the control, right? They have more fluorescence. That is absolutely normal. These two are normal. But if you see the 42, it has no fluorescence. That means there is deficiency of this CD42, that is GP1B9 receptor is deficient. That is Bernal-Soler syndrome. Clear? Then. And the same thing, if you do for GT, for a Glasman thrombasthenia, here, what will happen? Here the pink one, I'll use the pink color. Okay, the pink one. The pink comes here. Okay, in GT. In these two CD41 and 61, this is GT. The fluorescence the patient will not show any fluorescence. Okay, so the fluorescence, the patient will show fluorescence here, and the control will have the blue one. It will be here. This pink will come here in Glasman thrombasthenia. Same thing. But in Glasman thrombasthenia, we can use this markers to detect. And there is another method where they used to detect this Glasman thrombasthenia. That is another method is flow cytometric platelet aggregation. Flow cytometric platelet aggregation. This is the test name. Okay. So what they are doing here, they are assessing the function of the platelets. Okay, they are identifying the Glasman thrombasthenia. How? So here they are taking first the patient whole blood, then here we are centrifuging it. Why? To separate the platelets. Okay, because we are checking the platelet function, so we need PRP is platelet rich plasma. Platelet rich plasma. Okay, we are centrifuging it, then we are separating the platelets, we are making the platelet rich plasma. Okay, then after making this, they are separating into 2 different aliquots. Okay, 2 different aliquots, and by here we are adding CD31. Again, here we are not using markers, we are identifying the function of these platelets. What is the function of the platelets? Addition and aggregation, right? So we are observing this function, we are identifying this function, mainly the aggregation function we are checking by using the flow cytometry. So it is CD31 is not specific for any platelet marker, it is not a platelet marker, we are just using here CD31 to, and if you see here CD31, we are coating with different dyes. One is FITC, another one is picoerythrin. This is the green dye and this is the red color dye. We are using 2 different dyes and incubating the platelets. Okay. Then after incubation, then we are mixing them. See, A plus B, we are mixing them. Then, so what will happen normally when there is, when there is injury, the platelets first they'll adhere with the help of GP1B9 receptor. Then after addition, they will platelets get activated, right? And they will release certain chemicals like ADP, serotonin, epinephrine, right? Then what these chemicals will do, they will help in the aggregation of the platelets, right? This is all the basic hemostasis concept, right? So the aggregation will happen. The aggregation with the help of GP2B3A receptor, correct? So the same thing we are doing here, okay? So we made these 2 different colors, right? Then we are adding the agonist. Okay, agonist is nothing but, that means this, when these agonists, what they will do, they will cause activation of the platelets. These agonists are nothing but ADP or epinephrine or serotonin. Okay, we are adding this. What they will do, they will activate the platelets. When the platelets gets activated, what they will do, they will undergo aggregation, right? And how we will identify this aggregation in the flow cytometry, I will explain in the next graph. So can you see here the CD31, here this is not a specific mark, again I am telling, just we are adding two different dyes by using some antibody. Okay, so this is the picoerythrin dye, red color one, and the FITC green color one. Okay, two different dyes. So obviously the platelets which are tagged with FITC in the container A and tagged with picoerythrin container B, they will fluoresce with that respective dyes only when they get, right? So here CD31, the red color ones, only the red platelets which are incubated with picoerythrin, they will come here, and the platelets incubated with FITC, they will come here, correct? Then initially it will be like this. Then what we'll do, we'll add this ADP. Okay, what this ADP will do, ADP will cause activation of the platelets. So it does not, this ADP, there is no discrimination according to the dye. Whatever the platelet is platelet only. If it is dye, if it is coated with red color or green color, whatever, that's a dye. Okay, there is no concept of it here. There is the dye has no role here. Only to identify these double colored events only we are using the dyes. Okay, so here this ADP, what will do, it will activate these platelets and these platelets. Both the platelets are activated. Then once they activate, what they will do, they will aggregate, they will bind with one each other. So when this green and red, when they combine, what color will come? A blue color will come, right? So they will aggregate with one another, they will combine, and this blue color will come, and this is called double colored events. We will call it as double colored events. Two different colors they are mixing and they are forming a single event, that is blue color, and this percentage of this double colored events only they will calculate. So how will they calculate is the formula. So the double colored event in the Q2 region divided by the entire all regions Q1, Q2 and Q4, everything into 100%. Okay, so this we will do. So here if the blue color is forming means that is normal, right? Two different colors they are combined, that means platelets are aggregating. That's why green and red, when they are combined, that forms the blue color, that means aggregation is happening. That means the GP2B3 receptor is absolutely normal. So the patient is normal, healthy control. Okay, let's say if the patient has GT. Okay, the patient has Glasgow thrombocythemia, there is no GP2B3 receptor, so aggregation will happen or not? No, aggregation won't happen, right? Correct. So the same thing, initially we didn't add any agonist, initially we have done. So normal, the CD31 and 30, the FITC and picoerythrin, they are separated. Now we have added the ADP. Okay, ADP we have added. So ADP, it will stimulate the platelets. The platelets are stimulated, but they are not able to aggregate because they don't have the no GP2B3A receptor. So there is no receptor because the patient having Glasgow thrombocythemia. So there is no receptor, no aggregation, no blue colored events, no double colored events, no double populations. Can you see here around 0.6% only the double colored events, very less. Everything is impaired, the aggregation is impaired. That's why the patient is having Glasgow thrombocythemia. Clear? Understood? So this is it's a different mechanism. Same, we can directly use the markers and we can identify. It's a different, in a different way they have made this test, that is flow cytometry platelet aggregation test, the functional test by using the flow cytometry. Clear? Yes. So yes, we came to the end of the topic. So RBC disorders, WBC disorders and platelet disorders. Just again go through once again because it's a new topic. I know benign flow is like little bit new because flow we'll use mostly for malignant ones. Benign is very less. We'll flow cytometry will not see much of benign flow. So go through the video once again. Listen the video one more times so you can understand the concept and you can answer the questions. Okay. Thank you. Came to the end of the topic. Okay, then I will discuss another important topic in the next class. Till then, bye bye. Thank you.